So the goal of this talk will be to compute all correlation functions in SYK at strong coupling and at large n. So that's what we'll do. So SYK is a conformal field theory in the infrared at strong coupling. So it's hoped that there's an ADS2 dual theory, which we expect is something a little stringy, something a bit like Vasilyev. And the large n correlation functions I'll present through the ADS-CFT dictionary in principle fully determine this ADS2 bulk Lagrangian, the tree level bulk action. And with minor modifications, everything I'll say will apply to all variations, generalizations, and extensions of SYK. So these include, for instance, SYK with flavor, supersymmetric SYK, higher dimensional SYK, melonic tensor models, which are a new class of field theories, and lattice SYK models, which are being constructed to understand strange metals, thermalization, and chaos. So the solvability of SYK is tied closely to the structure of Feynman diagrams. So they're a small and well-organized set of diagrams, which we can sum at large n. So let me draw the diagrams, and then we'll sum them. So for the two-point function, as is already well known, we sum melons. So we sum all these melon diagrams, and what we find is that in the infrared, we have a CFT two-point function where the fermion dimension is delta. Delta is 1 over q, and for the picture, q is equal to 4. So after we've established this, we can, to proceed further with the higher point correlation functions, we don't care anymore that we sum melons. We just need to know that we have a CFT two-point function, and then we can proceed. So then we proceed to the four-point function and sum ladder diagrams. Such as these. And all the information about the four-point function after doing the sum will be encoded in a function which I'll call rho of h. I'll define rho of h in a minute. But rho of h has poles when h is at the physical dimensions of the ON bilinears, fermion bilinears, and roughly the residues of those poles are the OP coefficients of two fermions turning into one of the bilinears. So that's the four-point function. The six-point function looks like three four-point functions glued together. So that's the six-point function. By glued together, I mean one takes four-point functions and evaluates these integrals, and this gives the six-point function. Yes?
There's another way to do that.
That's right. There's another way. There's another class of diagrams which I'm not drawing, indeed. And all the information about the six-point function will encode in a function which I'll call C H1, H2, H3. H1, H2, H3 being the the dimensions of the bilinears here, here, and here, the fermion bilinears. I'll discuss that soon. And one of the main points will be that the diagrams such as this for the higher point functions. So let me draw it. So this is the 8-point function, one of the diagrams contributing to the 8-point function. And an essential point will be that this is determined by delta rho of h and c h1, h2, h3 through very simple rules. So after we've computed these three things, then we're almost done. Well, once one knows the rules. And the same follows for diagrams contributing to higher point functions, such as the 10-point function. So now it's clear what's happening. One just glues more and more 4-point functions, ladders, together. And what I said still holds. These three quantities, delta rho of h and ch1, h2, h3, the 3-point function of the bilinears, determines these diagrams, the ones for the 10-point function, and so on. So next, let me say more about the 4-point function, and then I'll tell you the higher point functions. So the 4-point function, so we can think about a general CFT. And represent the 4-point function as a contour integral. So a contour integral involving rho of h, which encodes our theory, and this quantity psi of h, which is a sum of a conformal block plus its shadow. So this is an SL2R block with 4 external fermions of dimension delta, and then an exchanged operator of dimension h, an exchanged fermion bilinear. So this function is familiar. It's just the hypergeometric function 2f1, just what we're used to. And this is the shadow block where one exchanges an operator of dimension d minus h, and in our case, the dimension of spacetime is 1. So this is an old way of, this is a less common way of representing 4-point functions in CFTs, but one can, I'm sorry. I should mention this contour. So this contour in H space consists of a line parallel to the imaginary axis at real value of 1/2, and circles at integers. So this is the principal series and the discrete series of SL2. So this is the contour appearing here. So the contour is not running over the physical dimensions. It's just the dimensions, these principal and discrete series, which are determined by representation theory. But what we can do is we can close this contour and pick out the poles of rho of h, which sit at the dimensions of the physical operators. And then we get a more familiar expression, just a sum of conformal blocks. I'm summing over the physical dimensions Hn, where Hn are the dimensions of the fermion bilinear Owen invariant singlets, the primaries. So these are schematically of the form just chi I, some derivatives in chi I. So this discussion has been completely general. The special thing about SYK is that we actually know rho of H. In H space, getting rho of H, one just sums the ladder diagrams. And in H space, the sum is very simple to do. It's just a geometric sum. Yes. But to proceed with computing the higher point functions, again, like with the two-point function, we don't need to know where rho of H came from, that it came from specifically summing ladders. One could imagine that one has some different class of theories where one sums something else, but one knows the four-point function, then one can proceed. Another point I should mention is that within the original SYK, it's not completely true that it's a CFT in the infrared. There's also the H equals 2 block, which is not conformal. And then one should add it here, and correspondingly in the higher point functions. So I won't be computing those terms, but one could compute them. Or alternatively, one could work with one of the variants of SYK that is conformally invariant. For instance, what David and I called CSYK, where C stands for conformal, which is, in fact, SL2R invariant for any coupling. Good. So now let me discuss the 6-point function. So it's clear how to compute the 6-point function. One simply takes 3 4-point functions and combines them, glues them together, which means evaluating some non-trivial integrals. And really what one is doing, since the 4-point function is the sum of conformal blocks, one is combining 3 conformal blocks to get the 6-point function. So for presenting the answer, it's more convenient to, rather than writing the fermion 6-point function, to write the fermion bilinear 3-point function. This has the same dynamical information. The bilinears being these O's. So this, of course, takes the form of a conformal 3-point function with 2 more terms here, which I won't write.
Are the C's defined only for the H's that are the dimensions of physical operators, or for any H?
Good. The C's are, in fact, defined for any H. In doing the computation, one nowhere needs to enter the fact that normally we only think of 3-point functions for the physical operators. So indeed, these C's are analytic. These are analytic functions of the H's and delta. So the C's are in themselves complicated. They take a page to write. They consist of gamma functions and generalized hypergeometric functions for F3. So I obviously won't write them. But several features to note about the C's. So the first one is what Juan said, that for the 3-point function of the physical operators, the h's take some very specific values. They're the dimensions of these operators, which are 2 delta plus 2n plus 1 plus some corrections, which we know from computing the 4-point function. But these c's are defined for any h's, and their analytic structure is very important. In particular, they will have, these c's will have poles at very specific locations, which are needed to give the right structure for the higher point functions, which we'll see once I write down the 8-point function. So that was the 6-point function. The 8-point function is the picture I drew there. So now it consists of 5 4-point functions glued in that way. And one might, at first, think that it would be very difficult to compute the 8-point function, since now there are simply more integrals one needs to do of combining conformal blocks, and indeed much harder since the, well, yes. And one of the surprising things is that there's, in fact, a very simple formula for the higher point functions. So for the 8-point function, and once again, I'll write the 4-point of the bilinears. So I'm writing the result for the diagram I drew up there. It's again given by a contour integral, the same contour as before. So let me explain this equation. So what appears here is the conformal block with external operators h1 through h4, these guys, with an exchange operator of dimension h. So that's what we expect. The 4-point function should be an integral or a sum of conformal blocks. Here we're integrating dh over this contour. It's the same contour as this one, as the one used to represent the fermion 4-point function. Again, what we would expect by representation theory. And what appears here is rho of h over c of h squared. C of h was essentially the residue of rho of h. And here we have c h1 h2 h. So if you look at this, so here we have h1 h2 h3 h4 coming in. And then we have an exchanged operator of dimension h. So C h1 h2 h here, C h3 h4 h here. So it's as if we have Feynman-like rules where the vertex is given by the 3-point function C h1 h2 h3. Yes?
Do you assume time ordering on the contour? The 8 points should be time ordered, right?
Yes. Yes.
Your calculation method will not work if they are out of time order, will it?
If they're out of time order, you should do something. I assume the OP is valid. So
Let's see, the 4-point function was valid for any time order.
the 4-point for any.
Why this one? I mean, here if you use the block and the shadow block, why?
Well, let's see. Maybe it's always true.
The first expression for the 4-point function is valid at any time order.
Yes, that's right. That's right.
The second one seems
this expression.
No, I just.
Oh, yes. Good. Yes, that's right. So indeed. So this is always true. When one closes the contour, one needs to say if it's time ordered or not. Well, if x is less than 1 or not, depending on. Indeed, that's correct. The expression that enters in computing these higher point functions, we always use this one for this reason, that the internal times, one needs to integrate over all of them.
But your h's are from the second expression.
No, because these h's are general. So this h you can take to be any number you like.
I see. So you can use the first expression with the h's from the representation theory.
That's correct. Here we have a contour integral over h, so the h's that appear here are the discrete series and the continuous one. It's not the physical ones.
I see.
So this expression is just true. Yes, let me take this back. This expression is just always true. Now, to get the 4-point function as the sum of conformal blocks, you would close this contour. And like with the fermion 4-point function, at the stage of closing the contour, you would then have to say if it's time ordered or not timed order. But this expression is just true. So now we get to the interesting part. So I didn't tell you how we got this equation, but it's actually easy to get. But one thing that we expect, and seems very non-trivial, is that the 4-point function should be a sum of conformal blocks. And in particular, it's a large in theory, so it should be a sum of single trace blocks and double trace blocks. So we need to see this appear from this expression, that when we close this contour and write the answer as a sum of conformal blocks, we have single trace blocks, double trace blocks, and nothing else. So from this row of H, as we said for the fermion 4-point function, row of H has poles at the dimensions of the physical operators at Hn. So this will give rise to the single trace blocks, because upon closing the contour, H becomes set to Hn, the physical dimension. So this will give poles at. So that's the single trace blocks. Very good. Oops. But we also expect double trace blocks. And what occurs is that this CH1H2, H has poles at H is equal to H1 plus H2 plus 2n. And these poles are what give rise to the double trace blocks, OH1 d tau to the 2n OH2.
Are these all the policy class, or it has more poles?
Good. In fact, it has more poles, which you would think would be a problem. But at all the other locations of the poles, row of H vanishes, and so they don't contribute. So it has just the right singularity structure to give the right answer. Well, at least the right form of the answer. So indeed, given how complicated C is, it seems like a miracle that it has poles in just the right locations. There's presumably some general property of 3-point functions in large N theories, that the analytically continued 3-point function, I'm not sure how one would define it in general, but the analytically continued 3-point function should have poles at these locations. So an additional comment is the calculation of the 3-point function of these coefficients C, H1, H2, H3, that was specific to SYK, the answer. But one could imagine combining 4-point functions in a different way, and then one would get a different C. Indeed, as Alexei noted in SYK, there's another way of gluing 3 4-point functions where they meet at a melon, and so one needs to include that as well. So so the 3-point function may change, but the answer I wrote for the 4-point function is just always true. It just relies on gluing 4-point functions in this way. So this is true in a general class of theories, not just SYK. Yes?
For the 8-point function, you can consider vertical letters in the middle.
Good. We summed those as well. So these are not all the diagrams. So for the 8-point function, there's this diagram plus two more, plus this diagram flipped in various ways. So like the ST and U channel, and one of them, so if you rotate it by 90 degrees, it's the diagram you said.
Right, and you should subtract the diagram with anything.
Absolutely, yes.
And all these are calculated in the same way, right?
Exactly. So just rotate, to get the other diagrams, it's trivial. It's just sending x to 1 minus x, or x to, yes. And yes, the final diagram you mentioned, in which there are no melons exchanged, it's also trivial to do. In fact, there's one additional. So going back to a general theory, so one special feature of SYK and this class of models is that these are the only diagrams. But one could imagine a general theory in which there are many other diagrams. So in that case, we would have summed a subset of them with this formula. But one thing I should note is that for the 8-point function, there's in fact an additional diagram, which I haven't included, which consists of 4 4-point functions joined together. So that one needs to compute separately, and it's straightforward to compute it. So this isn't the full answer. But it's the main piece of the answer. So a few properties to note. The first is there's universality in the sense that if one imagines considering, these functions, these 3-point functions, are analytic functions of the h's. So if one changes the h's slightly, for instance, by taking an SYK with a slightly different Q, or taking CSYK and going to different coupling, slightly different coupling, so the h's change very little, then the 3-point function will also change very little. And similarly, all the higher point functions, since they're just determined by the 3-point functions, will change very little. So in particular, in the limit in which the dimensions of the bilinears are large, when h is large, their anomalous dimensions are small. So their dimensions are roughly 2 delta plus 2n plus 1. And so these formulas imply that the correlation functions, so since their anomalous dimensions are small, it's like they have the same dimension as just these operators in a generalized free field theory of fermions of dimension delta. And so these formulas mean that all correlation functions of heavy operators will be the same as in this generalized free field theory of fermions. Yes?
For the other term in the 8-point function?
Yes, up to that other term, yeah.
What is the operator content of that contribution?
Just double trace.
So it's these same guys, h equals h1 plus h2 plus 2h?
Sorry. The diagram I didn't draw, where you have 4 ladders glued at a single.
Yeah.
That you have to, it won't involve the C's. Right. It's just a new calculation, but it.
I'm curious about what the operator content of that is. Like if you try to write it
as a sum of conformal blocks?
Yeah.
Just double trace with some coefficient. All the single trace have already been accounted for. Well, yes, it should just be double trace. So what was I saying? Yes. So the correlation functions of all the high dimension operators will be the same as in generalized free field theory of fermions. So I think what one can conclude from this is that all the strong coupling aspects of SYK, the chaos, etc., they're all encoded in the low dimension operators. Well, for chaos we already knew this, but everything special to strong coupling, you have to compute correlation functions involving low dimension operators. So one So one final comment with my remaining 0 minutes is knowing all the correlation functions determines the bulk theory in principle. So for the cubic couplings, the bulk cubic couplings are very simply determined from the 3-point functions of the bilinears. So the bulk Lagrangian will have some cubic couplings, phi n, phi m, phi k, where these phi n's are dual to the ONs. And in the limit where the dimensions of these, when the dimensions of the O's are large, what I've been discussing, the universal limit, and the masses are large, these couplings take a very specific form, which we know because we know the C's, which I'll write down. So the bulk cubic couplings, when take this simple combinatorial form. So any proposal for a dual of SYK must reproduce these couplings. And I draw your attention to how strange the couplings are. If one considers n equals m equals to k, so the self-interaction of the field of very large mass, this grows exponentially with n. That's not in contradiction with anything, but it's peculiar. All right, that's all. Thank you.